You have to keep linking, you have to find other ways. So I think my friend posted an article on his website. I think the most important impact is on this technology. It's not about finding new methods or technologies. You have to find other ways to continue linking. Only then can you find other ways to continue linking. May I ask Giovanni? Giovanni, I'd like to ask you to share your thoughts. Your detailed thoughts on the link. Yesterday, you heard Hedingbo's speech. Thank you for inviting me. I believe this design is a very powerful engineering work. It is a three-dimensional design. It will improve the efficiency of links. This design is very capable. In fact, we should control the timing of the three directions. We must remember that the problem is, it is not globalized. Because the speed of direction and the direction of straight rotation are different. And one direction is vertical. I think the concept of flipping itself is very interesting. I agree. My doctoral program discussed PLA inversion, PLA, a long time ago. At that time, people were doing PLA flips, but I don't think anyone did PLA flips this time. PLA. But again, it's a matter of using space in a better way to flip it. Therefore, there is a shortage of delay lines, a shortage of usage lines. This usually leads to shortages. Thank you. Doctor, please proceed. Thank you for your participation. This is a very exciting opportunity. I heard about the doctoral course, and this delay was very exciting. I think this is a very important new route for R&D business and academic internet. I attended the doctor's course, and he provided more details about the computer and AI center lines. AI. Therefore, I understand this logic better. I think this logic gives us a new space to make two logics become one system. I think this is very important. So, I think I have great respect for the doctor and her team. I think this is an exciting time. Of course, over the past 6 years, this has been a very difficult time. Because we did not receive the logic provided by the doctor. Therefore, I think this logic. I think we have this kind of logic. So, Doctor and Nanny, don't you mind me speaking Chinese? Nanny. I don't mind. I'm so excited, so I'll look into your eyes. I understand what you mean. Through a translator, we can understand how we feel. First of all, today I am especially excited to be able to sit on stage. Let's witness the announcement of our house law together. House law. As one of the earliest pioneers in the 3D-IC field, 3D-IC. Just as Uncle Li said. Actually, at first, Of course, I'll share a behind-the-scenes story with you. Liao Bo and I both worked under the same boss at Princeton. He is my senior brother, a first-year postdoc. I am a first-year PhD student. After we left Princeton, my first job was at IBM. At that point, I saw IBM working on 3D stacked punching technology. IBM 3D. So, at that point in 2003 and 2002, 2003-2002, IBM is already working on this technology, IBM. However, from the perspective of EDA and architecture design, there is still a blank slate. EDA. So at that time, I told IBM's mentor, I said that if this direction is to succeed in the future, shouldn't there be fundamental changes in EDA tools and architecture? EDA fundamental. He said yes, indeed. So in my second year at IBM, I decided to leave IBM. I joined academia, because only in academia can I conduct longer-term research. So during that period, just as Chunny Ran and Professor Chen just mentioned, between 2003 and 2010, 2003-2010. During this period, a lot of work was done, including folding the circuit layer. Folding at the core level. All sorts of things have been done. And at that time, we were also honored to be ahead of Intel. Semiconductor companies are doing this together. We folded the Pentium 4 into 2 folds together, Pentium 4. Then we stack 80 cores onto SRAM. 80 SRAM. But all these things exist in the work of research. By 2010, if everyone had the chance to see me, 2010. In 2010, I wrote a 3-page article, 2010. Basically, it's about 3D architecture, 3D. Are we there yet? When will we finally have jobs like this? Today, in the 15 or 16 years since 2010. 16 years later, with Huawei and HiSilicon truly integrating it into their products. I think this is an incredible achievement. Just like Kirin told us earlier, you actually published articles 20 years ago. Yes, we did publish articles. We have also done prototype designs. But when it actually comes to commercial implementation, I am very excited to see it. We achieved this with Huawei and HiSilicon. Liao Bai also mentioned a question earlier. Why didn't we have such a commercialized product at that time? I think there are actually many reasons. Actually, a very important reason is that at that time, Moore's law is still at 65 nanometers, then 65 nanometers, then 45 nanometers, and finally 32 nanometers, 65654532. It continues. So at that point in 2006, Intel has proposed an interesting model called the tick-tock model. Tick-tock. 1 year of architecture changes, 1 year of process evolution. This way, it can have new products every year. Based on the load mapping at the time, from 2006 to 2010 2006 2010. It means you can keep going for 20 years. But in fact, Moore's law is at 14 nanometers, 1/4. Suddenly, things calmed down. I think, looking back today, our TAU law is actually a further sublimation of Moore's law to its essence. Tau. It's not just about geometry scaling. In fact, Moore's law itself also implies the scaling of tau. Tau scaling. So I feel that seeing such work today, this is implemented in our HiSilicon chip. I am very excited and deeply impressed. Because during this process, from 2010 until now, 2010, I myself was involved in the design of this 2.5D HBM plus GPU at AMD. AMD 2.5D HMPU. Later, at Alibaba, we also helped Pingtuj develop chiplets, and we also worked on some test chips internally. Chiplet test chip. But in the end, commercialization has been achieved with today's Kirin chips. And including the Xia Jin Award Future Speaker chip. I think it's an incredible achievement. Thank you very much. So, since tile scaling law is a way to predict the future tile scaling law, the most important theme to discuss is: will this tile scaling law be sustained into the next century? Tile scaling law. In yesterday's and today's talks, we identified a host of biggest challenges. Some issues, if not properly addressed, may become obstacles. This could halt tile scaling. Tile scaling. So, I hope the audience has the opportunity to discuss these biggest obstacles and challenges. Including EDA design, including new memory and system integration EDA. Also includes chiplet and wafer scale design. And other ideas. For example, what is the impact of tile scaling? What impact does tile scaling have on computer construction? So I hope we can start discussing EDA challenges. Okay. I like this topic because it's at the top level. When you design a system, you can say it's ongoing. Because you want to upgrade it. So you need a very high-level barrier. This is a system with a lot of hardware. Whatever you do, you have to bring in energy. Then expel the heat. When things upgrade, from chips to servers, chip. Then to racks, then to data centers, and ultimately, racks. The biggest issue is energy input and heat exclusion. The second point is, you must have internet. So networking is extremely important. How to design networks and system bandwidth capabilities. In the end, there is a limit on how much data you can move. This becomes a ray of light, and the internet operates between different frameworks. If you do that, you'll drop even further, and of course, you will get a 3D fusion. 3D. Now, we see many benefits for EDA business, EDA. But I think you need a business boost. For example, Huawei, in the final process. They are doing these things to find out exactly which aspects. Further development is needed. Of course, there are still opportunities to test, timing tests. This is very important, especially when made from special materials. Go do these things. When you do these things, it becomes much simpler. When you reach the internet level, you get closer to the problems we have today. For example, if you look at the logic of EDA, it's not very complicated. It involves analysis, involves design. Design is simpler, but in my opinion, it's simpler than overall testing. It is simpler than the overall test. So, Giovanni, this will guide, Giovanni. This will lead to more integrated EDA tools across multiple stages. EDA. Because in the past, these designs were isolated. These designs and other testing functions exist independently. But in my view, the future trend is these designs will involve both analysis and design. In your view, these designs are all isolated. It's like a war. You work from one top to the other. This is true. When these designs are separated, I think. MACMA was the first in its design, MACMA EDIT. Isolated. It was a suitable design, and then became a further system. But now, you really have taken it further. The system you mentioned, the 3D system, is even bigger, 3D. There are more problems, possibly more difficult, and there is a salesperson providing solutions for many people because enterprises, just like you, and other businesses, you will eventually have different requirements. You're not talking about sales. You're only discussing the whole picture. Sales, internet, hardware, you want it to change. So I think we have to find a way. There is an internet of the internet, allowing people. A construction system like yours and a construction system like people. All the tools you can provide can be linked to those links. If you can solve all the problems, and at the same time, you have to find a way to split and attack the system. So, please. Yes, so most importantly, over the past month, Kirin, Siemens, and I spent time on design. Siemens. Synopsys, along with Siemens, spent time on design issues. Synopsys Siemens. So, my company has been in design phase for 20 to 30 years now. 2030. Basically, we looked at different design steps. Two questions are, when you design, what problems do you solve? But you cannot calculate design costs or design system costs. So the analysis and cooperation analysis we propose with these companies is using agentic AI, products with reduced design costs are at least 50%. We say this might be as much as 60%, 70%. Now, this doesn't change the design cost of business models. Yes, but they want to solve is. The first sentence is how to do system design. So, you do system design from the bottom up, and it doesn't work. You do system design from top down, and it also doesn't work. Because you have to improve chip performance, etc. But from what I've recently heard, it's about not improving chip performance in terms of time, which will significantly change the capability and demand for chip performance. Are they prepared? Of course, this is new. It just came out. By the way, although it just came out, I received many requests from large companies yesterday. What does that mean? I totally don't understand. I am trying to understand. But I think this will change from serious design to current design. In fact, it's from the small system level to the chip level, whereas previously we had two different levels. These need to be appropriately allocated by you. Of course, you not only need to improve chip performance and demand, you also need to improve your testing skills. So now you can do system layer testing, possibly, or even at the chip layer. So I think this is a big issue, systematically. It can affect chips, it can affect data centers. But I think it might take 4 to 5 years before it becomes a large-scale Moscow scale. But this is a big problem, from a design system perspective. Cadence, Synopsys, Siemens, Cadence, Synopsys, Siemens all need to change their design approaches. Of course, this is good news for China, because now you can develop chip manufacturing systems. You don't need to use the tools of Cadence, Synopsys, or Siemens today. Cadence, Synopsys, Siemens. You may have some possibilities for political restrictions. Alright, next, let's talk about electricity and heat release. Alright, we know that when the chip manufacturing system is in action, heat is produced, and the groundwork teaches us, guiding us on how to reduce electricity in direction. When you move data and some early work, the memory of these colleges is one way to reduce production. The movement of electricity, at least over distance, requires power to operate. But there are also memory fusion technologies, such as computational DRAM and SRAM plus theory. DRAM-SRAM. So, I think please share your thoughts about these differences, methods, as well as electricity issues and how to manage them. Iran, please. Iran. First, regarding solutions for calculating power or short-range power. Iran and Huaxiang are what we are doing. Iran. So, in the new application, first, we must power up our computers. So, our standards are low because you cannot provide data to it. So, if we have bigger data, we also have higher standards. This is a natural solution. So, we try to offer it in different applications, so we are strengthening power in new applications. Therefore, we are strengthening power in new applications. Because we are strengthening power in new applications. So, we once again improved our setup capabilities in new applications. So, you really do have that right in the new app. You can adjust iris and bottom up, iris bottom up. And tower up, further down. Tower up. One step further. Furthermore, I will continue translating. I want to explain it in Chinese. First of all, I think this question is very good. Chiplet wave scale. Or WSE, I think chiplet actually solves a big problem. WSE chiplet. Two questions. One is to frame the high bandwidth memory, and significantly reduce its costs. Then multiple chips can be interconnected together via chiplets, and so on. Chiplet. There's a question here that Xia Jin just mentioned. It's the problem of n squares and n. This might indeed be. You just calculated the numbers. I think your calculation is about 1 million or even a little over 100,000. 100. This difference in iOS is quite significant. I/O. So, at wave scale, we also conducted some research. Wave scale. Our college's teacher Hu Yang has also conducted a lot of research. In this case, you can see that in the wave scale, it is indeed possible to wave scale memory, whether it's SRAM or DRAM memory, SRAM-DRAM. By using 3D technology, it can also improve its bandwidth, 3D bandwidth. Locally, better handle this data and calculations, locally. Locally transferring is also very good, locally transfer. There are significant advantages. Advantage. So I want to. Recently, we've been conducting research, specifically 3D IC research. 3D IC. Frankly speaking, I think listening to Tesla today was still very exciting, exciting. Because in many past 3D IC surveys, 3D IC Most people probably integrate at the chip level integrate. Individual chip. Using an interface to increase bandwidth or improve performance is also a good idea. But in TOS-law, including Huawei's practices, TOS-law practice, I think the thing I learned the most is, learn. You design these several layers as a whole as one chip, Considering this issue from the architecture level. This issue is about looking at it from the perspective of time scaling. Problem. So I think this is actually for everyone working on 3D IC. Whether it's for weave scale or weave scale chip line. I think it gives a very clear optimization goal. This optimization goal is crucial for future EDA tool development, Or will they later develop memory, or will they do process work afterward? Memory. It can be said that they all provided a very good guideline. This is one of my feelings. Teacher Xia, would you like to participate? I want to add a few points. I want to ask, to everyone here today we're going to talk about Moore's law and nucleological's law. I want to test everyone and do a polling exercise. Polling. How many of you have read the original text of Moore's law? 3 pages of paper? My students should raise their hands, right? Of course you've read it, right? 3 pages of original text, page 3, last half page, last half of Moore's law, last half. What does the original text of Moore's law say? If you go further with Moore's law, what might be the biggest difficulty and challenge? It's the thermal and power issues that Mr. Liao just mentioned, thermal power. This is the kind of problem you encounter. Of course, he also brought up a second challenge. The second challenge is about the cost. So Moore's law is there, at the end of page 3. I wrote some suggestions. Suggestion. These suggestions are actually what we see today, suggestion. It means cutting big chips into small chips and piecing them together with small chips. In fact, to some extent, it's a chiplet. Or the way 3D stacks them, right? 3D. So in a way, Moore's law at that time pointed. Back in 1965, he had already made such a judgment, 1965. Predict that the most. Challenge 1, even for most. Law, is the thermal and power management. So today, I feel that regardless of what was just now. So today, we're looking at these chals. During eng, including the current large over hash eng, over hash. Ed data movement. So today I want to see the countless studies we have seen here today. Both the student and doctoral students' theses are about in-memory. Computing, or near memory. Computing, the purpose is to reduce the data movement, which is the major part of the power consumption for the chip design itself. So I think the current architectural innovation is also aimed at solving the thermal design and power issues. Of course, I believe there is another solution that may not be limited to the semiconductor level. There may also be microfluidic water cooling methods to solve this thermal design problem. I think this is also a very important. In short, I suggest that when we look at the new Tau law today, we are waiting for Huawei's article to come out, but at the same time, we are looking back. It has already come out. Right? At the same time, let's look back at the 3-page article on Moore's law from 1965. This is actually a very interesting correspondence. Alright, thank you. This situation is a bit different, because China now has a large supply of electricity. But the level of supplying more AI may lie elsewhere. Now, I believe that from Shakin's speech, he also reveals important facts. The model is different, because of China's DeepSeek model. It is a supply-price model of 1 or 2%. So this also demonstrates that the method of the model becomes useful. Because when you save the complexity of data, you also save time. So I especially want Professor Wu to share his ideas. He believes whether China has sufficient power supply. Does China have sufficient power supply? Yes. The power supply in China will reach $1 trillion by 2030. Of course, the latest forecast is that it will reach $1 trillion this year. Achieve $1 trillion in the market 4 years ahead of time. The primary power here lies with AI. AI's demand for semiconductors and computational power is very significant. As John mentioned, objectively speaking, when it comes to the electricity supply in the US, it is the most critical factor. So at this moment in China, perhaps the electricity supply may not be sufficient enough. But we can try different methods to support AI development, including model design. The design of models themselves might have various approaches to adjust the models. Or there are new models. Another approach, of course, is to design the model itself. Designing the model itself, of course, we face even greater challenges. Compared to NVIDIA, they can use the foundation of the highest technology, NVIDIA. And we don't have EUV, no foundation of cutting-edge technology. EUV. But I believe that now, through designing models. Or different design models, different methods for designing models. This actually gives us new space to support, even though we don't have EUV. We can still provide sufficient or meaningful power supply. Of course, I also believe that in China, the industrial chain, including design tools, they work hard too. Design tools are also working hard to make design models more powerful. So, it's very important that torch law actually goes from design models to systems. Torch law. So, this gives us the opportunity to get the greatest benefit. Due to the limitations of this design model, we gain the greatest benefits. So, I believe that now I can see many AI companies in Beijing, AI. Also in Shanghai, they are working hard. Of course, China has enough electricity. Actually, personally, I've been to many places. You can see a huge city, and also a huge apartment. This is actually China's advantage. I have also seen many public projects trying to build industry models, bringing the industrial model to the industrial center. So, I believe that in the next 3 to 5 years, AI enterprise suppliers will improve in China. AI. So, I think, in order to continue practicing the cycle of the times, especially from the perspective of industrial projects, this will require many types of gamers. Because it usually involves logical programs, as well as memory programs. It also involves industry suppliers who can combine these things together. Of course, our fourth player might be the system design player. Perhaps the master of the design system. Therefore, I believe that to continue practicing the logical procedures of the era cycle, the 4 forces we mentioned must cooperate deeply, collaborate more closely with others. So, I'm interested in what others think. What is the most important thing that can bring about such cooperation among multiple units? Be a successful and lasting relationship. Please. As a scientist, in the field of computer construction, I believe the computer construction area is actually crucial. The computer construction area is not just about the computer industry, but also about system construction. The computer construction area also enhances projects connected to software and devices. So I think at least in the future, in the continued execution of computer construction areas, builders should play a very important role. Leading EDA, packaging people, system construction, EDA. Software people develop collaboration. That's my view. I think my current position is yes. I think my perspective is a bit different. My view is, I believe, the builder's abilities. This is the key to the success of this concept. The builder's abilities, first and foremost, are very significant. Second, it is very effective. Third, system construction solutions must be at low cost. So, if you look at the current ecosystem, in terms of AI, it is a combination of TSMC, AI TSMC, NVIDIA, and its customers. NVIDIA. This is a triple relationship. I believe the theoretical differences are: compared to organizing enterprises and bringing about operations, it is actually a system-level vehicle. For this kind of construction, but system-level vehicles, in a sense, it is a supportive ability. However, you must have large-scale production capacity. I believe the biggest challenge is the equipment issue. How do you get the equipment to build production capacity? I believe that in China, production capacity is a key technology. Further improvement. 7 nanometers capability is sufficient. 7 nanometers. I believe that technological capabilities, from a technical perspective, is enough. However, you need production capacity. We discussed that, based on the current AI market, AI. 1.4 nanometers capability, you need 3 to 4 million vehicles, 1.4 nanometers, 300,400. Every month, in 2030. 2030. So, if production capacity becomes large, you would say, okay, 2030, 20% of the market, 2030, 20%. In 20% of the market, there will be 600,000 to 700,000 vehicles per month. 20%, 60-70. This is a great ability. If the market is 30%, of course it will increase again. 30%. So, our analysis is, we did an analysis. Production capacity supply in China. We started in 2020 and will continue to work in 2030. 20202030. In 2020, 10%, 5%, and by 2030, 60% to 70%. 202010%, 5%, 203060%, 70%. So this is a large production capacity in China. You need to produce 600,000 cars every month, as I said, 700,000 cars, by 2030. 702030. By 2035, 1 million cars per month. 2035,100. 2 million vehicles per month. So, I think, definitely, the most important thing is the fundamental capability of manufacturing. I feel this is the most important thing. That is the supply of production capacity. That is the supply of production capacity, insurance regulations, economic controls. I think these are the main factors affecting manufacturing capability. But I agree with you that the quality of manufacturing capability will continue to dominate. More than its supply capability, but it must be affordable. Affordable, not in terms of vehicle chassis level, but at the production capacity level. So, cost per token. Cost per whatever it is. The system lab will be key. Driver. So, I think we are running out of time here. Let me just summarize what we have heard. So, every panelist has found that switching from geometric scaling to time scaling, also across the 4 layers of systems, from device, circuit, and chip, all the way up to the system, opened up a brand new horizon. And for a much broader design space. So, I think, secondly, depending on the type of system we are looking at, once we have this multi-layer time scaling design space to work with, so far, we have found that there is a lot of ample room for shrinking time across the layers. So, the ceiling, we haven't found a blocking issue yet through all the several areas that we have examined during our discussion, although each system may have a different dominant tile to minimize first. And we believe that the scaling envelope can extend into the next decade or two. Thirdly, we talk about the manufacturing and the manufacturing ability and also economics of the tile scaling approach. And when we switch our optimization goal to minimizing or shrinking time, we found that the economics also need to come into play. Everybody, when we talk about a new architecture, We always keep the cost factor in mind, because a technology will not be viable until it is high performance.